In this lesson, we're going to introduce the topic of electricity by talking about electric charge and Coulomb's law. Here are your objectives. You've probably done the experiment where you take a balloon and you rub it against your hair, and then the balloon and your hair attract each other, making your hair stand up, and your hair repels itself, also making it stand up, and then you can stick the balloon to a wall, and if you do the same thing with a second balloon, then the two balloons, both rubbed on your hair, will now repel each other. They'll push each other apart. Now, experiments like this, rubbing different materials together, allow us to define the idea of charge and categorize everything into two categories, positive and negative. And that refers to the charge that they have, and they're really just arbitrary categories. There's nothing more positive about positive charges or more negative about negative charges. They're just categories. We could have called them red and blue, and in fact we could have swapped them. But historically, we've defined one set of things as positive and one as negative. And the important thing is that opposite charges attract, while like charges repel. So the balloon and your hair attract each other, but the two balloons repel each other. Now, if we then look subatomically, we can identify where that charge is coming from. In the nucleus, there are protons and protons have positive charges. And surrounding the nucleus, we have electrons, which have negative charges. Now, they have exactly the same amount of charge. One proton and one electron has exactly the same amount of charge, although they have a very different mass, protons being about 1,800 times more massive than electrons. Now, electrons move freely in conductors. So things like materials like metals, which we would call conductors, have electrons that can move freely and therefore carry electric charge. But electrons don't move freely in insulators. And so something like rubber, which doesn't conduct electricity well, has electrons that are relatively fixed in place. Now, the law of conservation of charge tells us that you can separate charges but not create or destroy them. So charges can be separated, and in fact that's what you're doing when you're rubbing the balloon on your hair, but you can't create or destroy charges. You can't create or destroy electrons. And equal numbers of charges, so equal numbers of positive and negative charges, are going to make an atom or an object electrically neutral. It doesn't mean that there's no protons or electrons in that object. It means that there's an equal number. The SI unit of charge is called the Coulomb, and given the abbreviation capital C. Now, a Coulomb is a lot of charge, and in fact the amount of charge on an electron or proton, again that's the same, is called the elementary charge, lowercase e, and that's a very small fraction of a Coulomb. It's 1.6 times 10 to the negative 19 coulombs. So again, because charge comes from protons and electrons, and one proton or one electron has this magnitude of charge, positive for a proton, negative for an electron, this is the smallest amount of charge you can have. We call this the elementary charge. All larger charges, therefore, have got to be integer multiples of this number. In other words, we say that charge is quantized. You can't have in between this amount of charge. You can't have things that are not integer multiples of this. But again, this is a very small amount of charge. It's the amount of charge on an electron or a proton. We said that the SI unit for charge is the Coulomb, and the law that tells us the magnitude of the force between any two point charges, meaning charges that are infinitely small, is called Coulomb's law, and that's given by the magnitude of the force is equal to a constant k times q1, that's the first charge, times q2, that's the second charge, divided by the distance between them squared. So the electrical force is equal to k, which we call Coulomb's constant, times q1 times q2. Each of those are the charges, and they're in coulombs. Be careful, it's not in elementary charges. It's in coulombs. Remember that because it's called Coulomb's law. And r is the distance between them, and r is squared. This is exactly the same form as our formula for the gravitational force between two objects, which was g, the gravitational constant, times one mass times the other mass divided by the distance between their centers squared. So again, it's an inverse square law, just like the gravitational force. The Coulomb constant, which is about 9 times 10 to the 9, is much, much bigger than our value of g, and that gives you a hint that the electrical force is much, much stronger than the gravitational force. Now, the force of the two charges on each other form a Newton's third law pair. So if you have a proton and an electron, let's say, and the electron is feeling an attraction from the proton is also feeling an attraction from the electron. Of course, the proton's more massive, so for the same force, it'll have a lower acceleration. Just to note that you'll also see the equation written in a different way, because Coulomb's constant is also equal to 1 over 4 pi times this other constant, which you might see called epsilon naught. That's called the permittivity of free space, and it has this value. So another way that you'll see Coulomb's law, in addition to the one written above, which is k times q1 q2 over r squared, is with the k written as 1 over 4 pi epsilon naught, or epsilon 0, times q1 q2 over r squared. And also sometimes you'll see q1 and q2 written as big Q and small q, just to keep them straight instead of using the subscripts. Just a note about the most common error people make with this formula. Let's say you're looking at a proton and an electron attracting each other. You might be tempted to put +1 and -1 for the two charges, but remember that these are the charges in coulombs that we need in the formula. So you need to put plus 1.6 times 10 to the negative 19 coulombs and negative 1.6 times 10 to the negative 19 coulombs. The formula requires coulombs, not elementary charges, so just be watchful for that. Okay, so that's Coulomb's law. Note that the equation of Coulomb's law, both forms, are for point charges, so infinitely small charges, but you can actually also use them for uniformly charged spheres. So if you've got large spheres where you've got positive charges all over one and either positive or negative charges all over the other, you can use it as well. R becomes the distance between their centers. And so that's actually exactly the same as how we use it in the gravitational force formula. Okay, so again, in that case, if this is the center and this is the center, then R would be this distance between their centers. Okay. Also remember that force is a vector, and so the net force from multiple point charges that are in a distribution is the vector sum of all of them. So if I have several charges, let's say I have a positive charge over here and a positive charge over here and I have a negative charge over here, and I want to know what's the force on something over here. Well, let's say this is a positive charge over here as well, so it's going to feel an upwards force from this charge down here. It's going to feel a force like that from this one. It's going to feel an attractive force from this negative charge over here, and then I'd have to add those three head to tail in order to get the vector sum of all of them, and therefore find the force on this positive charge here. Okay, so just remember that force is a vector. So that's an introduction to electric charge and Coulomb's law.